Currently like hiding in one of my closets right now using an old laptop because I have movers coming today. So I figured this will be the quietest place. So we'll try this right now and we'll see how well that's going. And yeah, we'll just go from here. So the laptop is like pretty loud with its humming. If there's like a problem with that, just let me know. But hopefully it should be okay. Cool. Let's go ahead and get started. So, last time we talked about moles and mass percent, right? We did all sorts of fun, goody stuffs about that. We talked about different compounds, different elements. This is kind of what we looked at last time here. Okay, so we looked at looking at mass percent, right? We looked at all of these fun, goody things. We talked about how the mole is going to help us to deal with really, really large numbers of atoms, which we do find that normal masses that we might use every day, do in fact have these huge numbers of atoms, right? And we saw like one lead atom was 3.4 times 10 to the negative 22 grams, and similar stuff. So we were able to do all this sorts of fun, good stuff with moles last time, right? So, cool. So we're going to go ahead and continue on then. Today we're going to kind of start by doing the opposite of what we did last time. Last time we kind of went from a formula to a mass percent, but we can do the same thing going from a mass percent to a formula. And we can go ahead and see what this is going to look like. Again, oh my goodness, this fan is like super loud. Can you guys hear that on this computer? We'll see. Okay, let's talk about it then. Let's talk about empirical formula of a compound. Alrighty, so the empirical formula is essentially what we're doing with this is we're going from the mass percent to the kind of the lowest ratio of atoms, which is what we call an empirical formula. Because way back when scientists were, kind of discovering compounds and classifying compounds, this was kind of the way to do it. So they would do combustion analysis. They would burn something. They would collect all the little bits that come out, and they would be able to find out kind of by mass how much of each element there was. So experimentally, they could come up with this information. And then they were able to kind of, using the idea of that the fact that compounds have fixed ratios of their atoms, they were able to come up with the what's called the empirical formula, which is the lowest ratio of elements to each other in a compound. And how this might work, if we were to take a look at something like maybe it was 89% oxygen and 11% hydrogen, which they determined experimentally. We'll say a compound they determined their mass percents to be these. And so what we're going to be able to do is figure out how to get this into a formula. It's important to note also that when we're talking about masses, which these would be, masses don't tell us anything about the number of atoms directly, right? We can't say, oh, well, I have 12.5 grams of carbon, so clearly this is 8 times 10 to the 23rd atoms, right? No, we have to do some math to figure that out. We can't just kind of look at it directly. So what we're going to see, the processes here is, if we're given percents like these, we can assume any kind of sample size we want, right? If we had a 1 gram sample, If we had 1 gram of this compound, well, then we would know it's 0.89 grams oxygen and 0.11 grams hydrogen, right? Because we know the percents by mass. But perhaps what's easier is, say, if we had 100 grams of this compound, we would have 89 grams of oxygen and 11 grams of hydrogen. When doing this, you can use any number you want. I think it makes the most sense to use 100 because then you can just go with those numbers. You don't have to mess with them. But if you really wanted to use 1 gram, that's fine. If you really wanted to use 3.7 grams, that's also fine. But then you're going to have to do some math, finding out what's 89% of 3.7. I don't recommend that. That's just a waste of time. So I think for our purposes, we'll just go ahead and use 100, right? It doesn't matter. The point is the ratios are there. And that's what we're looking at here. So if we want to think about these, okay, can we compare 89 grams of oxygen and 11 grams of hydrogen directly? And the answer here is, in red, no. So masses are something we've weighed out. They tell us kind of some physical information, but we don't really know anything about it. We can't just say, oh, well, this is clearly an 8-to-1 ratio of oxygen to hydrogen. No, it doesn't work that way because oxygen atoms and hydrogen atoms weigh different amounts, right? We know that oxygen has an atomic mass of 16 and hydrogen has an atomic mass of 1.008. So because these weigh very different amounts, you know, if we had different numbers of atoms, we can't say, okay, well, there's just a ratio there between these masses. Because these have different atomic masses. Each atom weighs a different amount. And so what we could do is we can either turn these 89 and 11 grams from grams into atoms. We could do that. But it might be a little bit easier on us if we just convert them to moles, right? We saw that last time. We could talk about a number as a number of atoms, or we can talk about it as a mole. And we saw that the one with moles is a little bit easier because we don't have the crazy exponents to deal with and all those, big numbers. So what we should do is let's go ahead and convert these to moles. And we can just do them kind of side by side here. So if we've got 89 grams of oxygen and we want to find the number of moles that is, again, if you want to do atoms instead, you are more than welcome to. But moles is easier. We know that each mole of oxygen would weigh 16 grams. Again, this number is from the periodic table. That is our atomic mass from our periodic table there. And we could do the same thing for hydrogen. Except we would use its atomic mass instead. And I'm going to be very consistent when I'm using oxygen and hydrogen so I can keep things straight as I calculate. And we can go ahead and do the math. So we have 89 divided by 16. If my computer wants to behave. There we go. 89 divided by 16. We get 5.5625 moles of oxygen. And if we do the same thing for hydrogen, 11 divided by 1.008, we get 10.91, let's just say 3. I know I'm rounding these, but we're going to see it doesn't matter because these aren't measurements. We're not going to be coming up with numbers at the end, or the numbers that we are coming up with are integers. So I don't have to worry about that. So With these now, this tells us that for every 5.5, we'll say, moles of oxygen, we have roughly 11 moles of hydrogen. Just looking at those numbers kind of as is. And if we want to find the lowest ratio between them, I mean, this is saying essentially we have a 5.56 to 10.91 ratio. But who the heck says that, right? We like to use integers. So what we can do, if we want to find the lowest ratio, we can just divide by the smaller number, right? And that'll give us our smallest ratio. So if we go ahead and divide both of these by the smaller number, I mean, that'll be 1. And let's see, I'll actually do this. It's going to be a little off because I just guessed on these, but that's okay. 10.913 divided by 5.5625, and I hope it's close enough. So we got about 1.96, which is close enough. We're going to see when to round these and when not to round these. That's about 2, right? And the reason that it's not so exact of a number is because I only gave us 2 sig figs to start with, the 89 and 11. And so this finally tells us something. For every 1 oxygen, we have 2 hydrogens. And so this mystery molecule is 2 hydrogens, 1 oxygen. That's the lowest ratio we have. And so the empirical formula for this compound is H2O. Ta-da! So remember, we can't compare mass directly. Mass we can get from experiments very easily. But we can't use that directly when we're actually working with these numbers, because each atom of every element weighs a different amount. So we need to take that into account here by kind of neutralizing the playing field by converting everything into moles. Again, if you want, you can convert them to atoms instead. You're just going to have bigger numbers to deal with, but you will get the same answer. And we're going to see here this is essentially just a process. So it's not terrible. We'll do a couple of examples here, and we'll go from there. So here's one for us. Let's say we have something that is 43.4% sodium. Let's do another example. It's 11.3% carbon. Sorry, there's a decimal there. And there's also 45.3% oxygen. And generally, while I kind of didn't do that in the first example, I'll generally give these to you in the order that you should write the formula. So, like, for example, you'll write sodium first, then carbon, then oxygen in your formula. So we'll do that. So, step 1. Remember, percents can be from any mass sample we want. If we wanted to use the 3.7 grams, go right ahead. If you want to use 100 grams and save all that time, look what we can do. Poof. Now they're all grams. If we just have a 100 gram sample of it. Remember, it's all about the ratio. So I can choose whatever sample size I want. So I'm looking at 100 grams because that's the easiest to do. Ta-da! So you can either be given grams or you can be given percentage. Doesn't matter. If it's grams already, go ahead and use it. If it's percentages, just erase the percent and write gram instead. So, makes things easy. So, I'm actually going to separate these out a little bit, though, because I realize they're going to be a little clustered. Be a little easier if they're just moved a little bit, just so I have more room for the math. And so with all of these, again, with masses we cannot compare directly. So we need to look at them as moles. or atoms again. I will always choose to look at moles instead of atoms because I like reasonable numbers. And so we're going to see, well, we know oxygens from last time. If we find carbon on the periodic table, we'll see it's 12.01. Remember, all these three numbers come from the periodic table. So I'll just note that. All these numbers, these are all our atomic masses. So we need to convert all these things into moles. So all of these blue bits here, those are atomic masses from the periodic table. So let's go ahead and take a look at that. If we go ahead and do this, I don't even have my calculator in this room, but that's okay. So let's do it. So we have 43.4. Sorry, you're going to see my fingers because for whatever reason this laptop has the camera like at the bottom. So that's also why you're seeing so far up into this closet. So it's fun. Okay, so for sodium, we get 1.887, or let's just say 8 moles. Again, I'm rounding here. That's okay because we're not going to actually be using these numbers to do any like math. So for carbon, 11.13 divided by 12.01. We get 0.9409, we'll say. And then for oxygen, it's 45.3 divided by 16. And that gives us 2.831. So we now have our kind of ratios. Remember, you can't use these as is, although in this case it's going to kind of work, but we're not going to be able to just use these numbers as is, right? If we want a ratio, we ideally will divide by the smallest number of moles. Maybe you can see right now it's probably a 2 to 1 to 3 ratio. Like they're all just a little bit below those numbers, and in fact that's what it will be, but don't trust yourself on this. You're going to always want to be systematic about it and do your math. So we're going to divide these all by the smallest number. And I'm going to just go ahead and say, yes, these are the numbers we get. These should be pretty exact. Like it might be like 2.999. That's close enough. And so with that, we'll see that we get 2 sodiums, 1 carbon, and 3 oxygens out of this. So these numbers, again, we have 2 for sodium, 1 for carbon, 3 for oxygen. And those numbers, for example, go down here. Like, that's what all these mean. So, if I don't put a subscript, that just means 1, right? So, we're just kind of using now what we've calculated to determine the formula of the compound. And it works. So, hopefully so far so good. I'm going to tell you now, though, if we actually look at that oxygens, let's go ahead and say 2.831 divided by 0.9409. If we do that, technically this number was 3.008. Hopefully we'll see that it is reasonable to round this number to 3, right? It's pretty obvious, right? And so I'm going to give you kind of a rule that you can use to determine when to round. And we'll see this in our next example, that I've cooked up one that we're going to end up with not integer numbers. And really, the only time you're allowed to round is when you are within 0.05 of an integer. Other than that, I'll show you what to do. Let's take a look at another example, and we'll see what I mean by what the heck do you mean by rounding the ratio, and we'll see what to do. So, here's one. We have a compound that is 57.2% sulfur, and the rest is oxygen. Well, sulfur one we can handle, right? Oxygen, we're going to have to do a little bit of easy math. If 57% of the compound is sulfur, well, the oxygen would just be then 100% minus that, right? Which would give us 42.8% oxygen, right? Since they have to add up to 100%, right? So there we go. Done that bit. So let's go ahead and figure out its empirical formula using much the same method as we just did. So 57.2 grams sulfur, 42.8 grams oxygen. We'll need to convert these to moles. For sulfur, the atomic mass is 32.07 grams. Again, use your periodic table. I happen to have these memorized. Don't do that. I have only memorized it by using them so many times for teaching over all these years. Don't ever waste time memorizing these numbers. You'll always have a periodic table. So that's sulfur. And this will be oxygen. Whoops. Got all the way up there. Sorry about that. Okay, let's go ahead and do this. So 57.2 divided by 32.07. I get 1.784. And let's do the oxygen one. So 42.8 divided by 16. I hope I did my subtraction right. I get 2.675. Okay. So here we are. Now, again, we want to divide by our smaller number so that we can get a ratio out with integers. So we can do that. With these, of course, the smaller one becomes 1. We don't need a unit there, so 1 sulfur. And then let's do this one, divide that by 1.784. And we get 1.499. And so would we say, oh, well, clearly we should just round this to 1, right? No. Can't do that. If your numbers are not within 0.05 of an integer, you cannot round them. You can't say, oh, well, it's close enough to this integer and I'm going to just round it. If you have something like this, you're going to see you'll want to multiply them. So we have essentially here a ratio of 1 sulfur to 1.5 oxygens. If we want to get rid of that 0.5, we can just kind of multiply all this stuff by 2. And if we do that, we'll say, oh, let's see, it's a 2 to 3 ratio. 1 to 1.5 is the same as 2 to 3. So you cannot round unless it's within 0.05. This is 0.5 away from rounding. So cannot round here. And you're going to have problems if you just say SO, because that's not the ratio. So we're going to see there's kind of a handy-dandy thing to multiply by. So if you have something 0.16, you'll want to multiply by, you want to multiply everything by 6 if you have something that ends in 16. So these are going to be like with your, whatever your ratio ends up with. If you end up with something that ends with 0.16, you'll want to multiply by 6 to get rid of that decimal. So just like here, we had something that ends with 0.5, we're going to multiply by 2 to get rid of it. It's the same idea with 0.16, but we'll multiply by 6. If you have something that is 0.25, you'll multiply by 4, of course. If you have something that ends with 0.33, you'll multiply by 3. If you get to 0.5, you'll multiply by 2. If you get back 0.67, you'll multiply by 3 again. 0.75, you'll multiply by 4. And what's the last one? 87, I guess. That'll get you to multiply by 6. So these are common like things you might find. In this case, we had this one, right? We had something that was 1.5. So we want to multiply everything by 2, and that'll make it into integers. If nothing else, if you want to just try things, you can keep trying to multiply your numbers to see what you get out. You want integers. And if you don't get exact integers, you want them within 0.05. We saw with the previous one, this oxygen was, we actually got 3.008. It is fine to round that to 3. That is within 0.05 of 3. So we can round it. That's okay. If we ended up with 3.16 or something, that we cannot round to 3. We would need to multiply everything by 6 in this case, had that been what we had gotten there. So just keep in mind for rounding purposes. Somebody students will say, okay, well, it's 1 and 1.4, those just 1 to 1. And it's like, no, it's 1 to 1.5. And so you'll want to multiply everything by 2 so that we can get actual integers there. Okay. Any questions on those? All right. Rather, let me change that. Most of the time, we're going to see that most of the time, in reality, compounds have chemical formulas that are not empirical. For example, this guy, let me write that again a little bit more clearly. This is hydrogen peroxide. We've heard of this before. Hydrogen peroxide does not have an empirical formula, or it is not an empirical formula. Remember, an empirical formula must always be the lowest ratio. So 2 to 2 is not the lowest ratio, right? It's the empirical formula for this would be just HO, right? A 2 to 2 ratio is not the smallest ratio we can make of it. We would make it instead a 1 to 1 ratio. One hydrogen, one oxygen. That is our simplest ratio we would have. And we're going to see that this is the case for a lot of things, where they don't have kind of empirical formulas. They have what are called molecular formulas. So that there is an example of a molecular formula. All empirical formulas are molecular formulas, but not the other way around. So an empirical formula has to have the lowest ratio. A molecular formula can have whatever ratio it wants. For example, H2O2. It's not the smallest ratio. It's still the same ratio, though. It's still a one-to-one relationship, but in this particular molecule, you have to have exactly 2 hydrogens and exactly 2 oxygens. So the molecule hydrogen peroxide has 4 atoms total. But if we were to just say we burned this, we would end up with an empirical formula that's just 1 of each. So empirically, we can only get the lowest ratio. But oftentimes, things are multiples of that ratio. Those are molecular formulas. And so in order to kind of get past that, in order to get from empirical formula to molecular formula, we need the molar mass of the compound. So, what the heck does that mean? Well, molar mass is also something we can calculate experimentally. In this class, we will learn one way how to do that, for gases specifically. But if you continue on with chemistry, especially if you go into 113, which is Gen Chem 2, that class we learn a ton of different ways to experimentally determine the molar mass of a compound. And so we just need one more piece of information, and that can take us from an empirical formula to a molecular formula. For example, the compound with an empirical formula, I'm giving us the empirical formula this time, I'm going to make it a little easier. HO is found to have better? I think so. Okay, I'm registering sound now, so please let me know if that's working. And then also, like, did it just cut out, like, right now? Okay, good. I'm glad it's working. How long has it been since it's been without sound? Hopefully just, like, a couple of seconds. Again, yeah, I'm using this old laptop. 5 minutes? Oh, shoot. Okay. Well, all right. So let's scroll up here then. No, no, no. Oh, I get that. So when we like maybe was it about starting in this area here where we were talking about going from the molecular mass to empirical mass? Is that it, or a little bit before that maybe? And I can just talk it through it again. So about here. Cool. Okay, so I'll just restart all of that. Sorry if it's a little redundant, if I still cover some stuff. Thank you for letting me know about that. So, cool. When we are given an empirical formula, or we've calculated it, sometimes we're going to see that a real molecule might have a non-empirical formula. So an empirical formula, remember, has to be the lowest ratio, HO, for example. But a real molecule might have a molecular formula, H2O2. And so in order to kind of bridge the gap between those, we need more information. We need the molar mass of our compound. And that's something that's always going to be given to you because that's something determined in a different experiment. So in this class, we'll learn one experiment that we'll use to determine molar mass of an unknown compound. But if you keep taking chemistry, you'll find out a lot more. So cool. So in order to figure out your molecular formula, after you've figured out your empirical formula, what you want to do is compare their molar masses. So you'll be given a molar mass of your molecular formula, of your molecule, the actual compound. The empirical formula you can determine using the mass percents, like we've been doing. And then you can figure out the molar mass of your empirical formula by just adding up the atomic masses of the elements there. So for HO, for example, if that was a empirical formula I was given, I could find its molar mass by adding up those two elements. And so doing that, I get about 17. In this question here, we're told our empirical formula is HO, but our real molar mass is 34. And so what we want to do is compare those numbers. So we've got this 34, that's our real molecule. We've got 17, which is our empirical formula. And so if we just compare those numbers, we see, oh, well, that one's just twice as big. Our molecular formula is twice as big as our empirical formula, which therefore tells us that we just want to take our empirical formula and essentially multiply it by 2. Because our molar mass is twice as big. And so as a result, we end up with our molecular formula of H2O2, which is the one that we're looking for here in this particular problem. Alrighty, cool. And then so if we then want to do this again, taking it one step further, where again I'm giving you the molecular the molecular molar mass in the question. And now I'm giving you a way to find the empirical formula. And so the first thing we need to do, because the last question I gave you the empirical formula, the first thing we're going to need to do here is determine that using the numbers that I've given you. And so we're going to take that 40% and the 3.36% for those two elements. We are also told the rest is oxygen, so I did a little bit of subtraction there. And hopefully that's a subtraction. So I figured out it was 56.64. That was missing there. And so now if we want to go ahead and convert those to moles. Now we can go ahead and do that. So, cool. So now we're kind of caught up. So we had a moment there where we had no sound. On this computer, also, it's not showing the chat box, but in the chat box, one of your fellow students had let me know the sound wasn't working, so I backtracked a little bit. So, I guess after seeing this, you'll find out there's sound again. So, sorry for making you all go crazy. Maybe in the title or something for the video, I'll be like, there are 5 minutes without sound or something, and then we'll deal with that. Cool. Anyways, let's go ahead and do this empirical formula business. So, let's do it. 40 divided by 12.01. We get 3.33. If we do the same thing, 3.36 for hydrogen divided by 1.008. We get 3.33. $56.64 divided by 16 is 3.54. Because I've done this problem wrong, I need to change the percentages. I think when I was setting up this problem, this is not what I intended it to be. So let me just backtrack on this. Should not be 56. This number needs to be doubled here. So let's say it's 7.72% hydrogen. Let's go ahead and change this problem. Okay. Sorry, I lied to y'all. We have to fix this. So 52.28 then percent oxygen. Okay. Sorry. With these ones I can't make up. I have to plan these particular problems in advance to avoid these problems, but lo and behold, I still made a mistake. So doing this, there we go. That'll fix that. And now let me go ahead and do 52.28. And hopefully that should give us the answer we're looking for. Good enough. So 3.27. Okay. So this is for our carbon, our hydrogen, our oxygen. Again, here we can probably see it's a 1 to 2 to 1 ratio, but let's go ahead and be diligent and actually divide by the smallest number. And we'll see why we're able to round this one, I hope. 3.27. We get 1.018. That is within 0.05, so we're allowed to round that. If we do the 6.66 instead, we get 2.04. Again, within 0.05, we're okay here. And then there was just going to be 1. So these are close enough to be rounded. I'm going to just make a note of that. These are within 0.05 of an integer. We are okay to round. So we can say 1 to 2 to 1. So our empirical formula, therefore, is CH2O. That is our empirical formula. We've calculated this. We have 1 carbon, 2 hydrogens, and 1 oxygen. And so that is our empirical formula. However, in the problem, we are told that we have a molar mass of 180.2. And so we need to take that into account when we're working with our numbers here. If we think about this, what's the molar mass of this guy? If we do that, we have to do carbon plus 2 times hydrogen plus 1 times oxygen. I guess I could say 1 times carbon, but why bother? So 12.01 plus 2 times 1.008 plus 16. We get around 30. Do I want to actually calculate this out? 30.03 perhaps? That seems about right. Always check my math. Sometimes I make oopsies. But this one, that's what I'm looking for in this problem anyway. If we see our molecular mass, remember that was given. Hopefully we can see here, but let's go ahead and see. Aha! Well, 180.2 divided by 30.03 is about 6, right? 18 and 3. 180 and 30. Which means that we need to multiply our empirical formula by this thing, by 6. And so our molecular formula becomes C6H12O6, which is glucose or fructose or many of your other simple sugars. So again here, this is a molecular formula. Molecular formulas are not empirical. They can be, but it's not true in this case. Our empirical formula was CH2O. That's the lowest ratio. But we know that a molecule of glucose has 6 carbons, 12 hydrogens, and 6 oxygens, no more, no less. So that's how we're able to figure this out. So, any questions on that one? So, that is our empirical formula goodness here. So, we're in good shape. This is as far as you'll need to go for your exam that's coming up. This is kind of the end of material for exam 1. Hooray, which is on Monday. Yes, Monday. So we're good. We're kind of good where we need to be for this exam. Although we will probably want to start. Do we want to start chapter 4 today? No, I don't think so. We can start chapter 4 next time. So I think this will be a good place to close, because chapter 4 is going to take us into very conceptual territory. I think it would be good to just kind of stop here for today. So we'll work with that. And again, I apologize for the microphone snafu. So hopefully I'll only have to use this kind of laptop in the closet thing for a couple of days, and we'll hopefully be back to normal. Otherwise, we'll figure out something. So I think that's good for today. So there is homework on this, on empirical formula and moles. So you'll want to check on that. Let me just make sure. Oh, I don't have Canvas open. Never mind. You should have a homework assignment on molar mass, empirical formula, all that sort of good stuff that you can be working on. So I would suggest you go ahead and start doing that. Your exam will have everything from the beginning of class up till essentially right now. So this goes into chapter 3b, the end of chapter 3b. We'll start chapter 4 on Thursday, and we can go from there. So let's see. Do we have any kind of questions about the exam or the material so far that we'd like to go over? Wow, the blue light is like crazy. I get the blue eyes here. So this material, I get, it's pretty theoretical. There's some, unit conversions. There's some uh, calculating molar mass. It's a pretty simple exam in terms of like material you need to know, but there is still a good bit of a material. So don't forget your stuff from the beginning. So when we talked about matter, when we talked about how to convert between units, those metric conversions, don't forget those. Let's see, what else do we have? Setting up dimensional analysis, unit conversion properly. Talking about atoms, the numbers of protons, neutrons, and electrons. Don't forget those. What else do we have? We talked about classifying matter. We talked about states of matter. We talked about physical properties, physical changes. So all those things, don't forget them. You have an exam on Monday, so it would be good to work with those. All right. Alrighty then. That'll be it for today then. So if there's questions, as always, throw them in Discord. That's our best place to do it. I do recommend that you guys, you're totally welcome to post like screenshots of your homework and stuff in Discord for asking your classmates for help. It's a good idea. I don't mind if we work on homework problems together in Discord, because that'll help everyone. So don't be afraid. Everybody's got questions, so just post them there. Again, if you really are super shy, you can just message me directly, but it is more beneficial to everybody if you just post your questions in the general thing, because believe it or not, a lot of you do have the same questions as each other. So it's just easier that way, and then everybody can see and benefit from them. So cool. Alrighty then. Enjoy the next couple of days. We'll continue on Thursday. Thursday's material will not be on the exam. We're starting a new chapter. And so we'll just go from there. Okay? Alrighty then. Enjoy your day.